So I think we can kick it off. Let me just admit people, and let me briefly introduce Ishan. For those of you who are in computer vision, he probably doesn't need an introduction. He's a research scientist at Meta in the recently formed Gen AI team. As far as I understood him, that's a new team that just was generated, I guess, after Llama was announced or something like that. You can tell us a bit more about the timelines there. You're the author of the Dino paper, which I think a lot of people know, and also Barlow twins. And today you're going to be talking about, I guess, video generation work recently, like the emu video, among other things. So without further ado, you can kick it off. Thanks for joining.
Hey guys, I want to give a huge shout out to Hyperstack folks who have generously sponsored my compute over the past month or so. Basically, I got 16 H100s, which is 2 8 GPU nodes, and the performance has been amazing, basically 2x the speed up compared to my A100 nodes. So I want to quickly show you how you can get started yourself. It takes basically 3 steps only. You go to the environments here, you create a new environment, you give it a name, you pick between Canada and Norway. That's the first step. The second step, you go to SSH keys here, you create a new pair, you pick environment you just created, you give it a name, you paste your public SSH key. That's it. And finally, go to virtual machines, deploy new machine, give it a name again, select environment. Let's select Canada here because they have more compute there. Then you select the hardware you want, like for example H100s. You select the images, you select the SSH key you just created, and hit deploy. That's it. Literally a couple of minutes to get started. It was really easy for me to just basically create these 2 nodes I just mentioned and get started running LLM trainings. So the documentation is super cool. I could actually solve all of my problems just by looking at their docs. They additionally have a Slack channel where they were super helpful, so I can't recommend them enough, honestly. The thing they kind of focus on is basically, because a lot of these GPU providers focus on big enterprises, so oftentimes you can't get on-demand H100s, whereas NextGen focuses particularly on that. You can get top-of-the-line hardware on demand, even if you're an individual or like a smaller team or whatnot. They also focus on bigger companies, but that's kind of their edge here. So without further ado, guys, let's go back to the talk. I do suggest you check them out, and let's continue.
Cool. All right. So, I mean, this group needs an introduction, sort of context here, but in this era of multimodal learning, we have basically seen that getting aligned data where you have billions of image and text pairs really sort of fuels a lot of the current models, right? So when we get lots of these billions of image text pairs, we are able to learn representations that align images with text. So CLIP being one of the most standard examples of being able to do this in a really sort of large scale and actually getting high quality representations. And these aligned representations have been super, super useful. So they've sort of fueled other applications like image text retrieval, detection segmentation, and even like generative models. And really, whenever I talk about my work and having worked in self-supervised learning for a while, there's always this question that people keep asking me, which one do you prefer? Do you want to do self-supervised learning? Do you want to do weakly supervised learning? Do you want to do supervised learning? And it's always seen as a competition, right? Like whether you can do one thing or the other. I think if you think about it from terms of papers and the way this research is presented, it's always that you do either SSL and there's a paper about SSL like Dino V2, or there's a paper basically sort of using lots of data, supervised data, and then doing that at scale. So like CLIP, SIGLIP, and so on. But I do think there is actually a common ground between them. And so SSL and weakly supervised learning can actually be combined to do lots of great things. And here are a few examples of some of the things that we did at our work that show that self-supervised learning can actually be combined with supervised learning to yield much better models. And so as one of the simple things, you can actually use self-supervised learning to initialize your models that will then be used with supervised learning. And we call this thing as pre-training because we can do this at like really, really large scales. We can also use self-supervised learning to combine and scale models to multiple different modalities. So to go from just like 2 modalities to like 6 or 7 modalities. And finally, SSL is really sort of, I think, one of the guiding principles for doing generation. A lot of the generative models that you see are, I would argue, doing self-supervised learning in some form or the other. And so just to give you an example of how you can combine self-supervised learning with weakly supervised learning, this was a paper that we had at ICCV last year, which shows that you can take MAE, which is masked autoencoders, and use that as a stage for called pre-training, and basically then initialize these models and then perform basically billion scale pre-training, which is the standard sort of image text or image label learning. And the key idea here is that this pre-training stage is going to be completely self-supervised. So we're going to use MAE to do this pre-training. And then once we have done this pre-training, then we initialize this model, and then we'll train it just in a standard sort of manner. So here are the sort of two stages. In stage one, we basically take pre-training. So we use MAE, and we take the standard data that we have. So in this case, the internet images. And then we feed them through an image encoder. We basically do the standard MAE trick where we are trying to reconstruct the masked patches. And because of the way MAE uses an asymmetric encoder-decoder architecture, we can actually have very low flops for training, because we can do 75% of the image masked, and then we can feed that through the encoder, and then try to basically, the encoder is only operating on the unmasked patches, so it really has very low flop utilization, low flop requirement. And for the step two, once we have this image encoder trained, we can then do the standard sort of multi-label learning or contrastive learning or any other thing. In this work, we basically decided to do multi-label learning. And then you can use the final model, this image encoder, for doing all your various downstream tasks. So here's the pre-training setup that we tried at scale. So we used a data set of 3 billion unique images from Instagram. And after sort of sampling and making sure that we're oversampling the tail and have a reasonable distribution, we get about 5 billion images. For the weekly supervised stage, we have 28,000 unique hashtags. So these are just hashtags that you can think of as class labels. Sometimes these can be a bit more noisy, of course, than class labels, but we have 28,000 of them, so that is pretty large vocabulary. And the architecture we'll use will be vision transformers, scaled all the way up till 6.5 billion parameters. So the first thing we observed is that basically this pre-training really helps models across different scales. So here on the x-axis, you have models of different parameters. So going from 100 million parameters to 6.5 billion parameters. And in the blue line, we have the standard supervised learning. So if you were to use the 5 billion images that I talked about and basically just start training a model, this would be its downstream performance on ImageNet. And in the green line, we have our pre-training setup, where we have initialized this model with the same images, but in an unsupervised manner. And then we're basically doing the same thing of like basically training it on the 28,000 way classification setup. And what we find is that at every single stage, the pre-training model actually outperforms its weekly supervised or its supervised counterpart. And in fact, you can see that at the 2 billion stage, the pre-training model actually outperforms the 6.5 billion, a larger model, in terms of its ImageNet accuracy. And so with the same amount of data, so there was no extra data used for this pre-training stage, self-supervised learning actually starts giving you gains. And the gains do seem to get better and better as the model size increases, which also is a pretty good phenomena here. You're not actually seeing saturating gains.
Just a quick question
other thing that
on my side here. Sorry for interrupting.
Yes.
Are there any scaling laws for vision transformers right now, like similar to what we have for LLMs? Like how many images do you have to have like per parameter or whatnot? Is there anything similar that was discovered recently on that front?
So not to my knowledge. I think basically the setups are depending on the type of like data distribution that you're going for. I think these answers are going to vary a whole lot. And I don't think there's been a huge amount of like rigorous study like in LLMs for vision transformers.
And do you do like a multi-epoch training here, or you just like do one pass over 5 billion images?
Yeah, so I think this slide kind of answers that. So we do like a multi-epoch, but basically within the first epoch. So over here you see number of pre-training epochs. Within the first epoch, you are able to get like most of the benefit.
Thanks.
And so here's where this pre-training also is quite useful, right? So depending on the number of pre-training epochs that you're doing for weekly supervised learning, pre-training, just a very small amount of it. So just pre-training for like 0.1 epochs actually does much better than weekly supervised training for 0.4 epochs. And so essentially at every single stage, no matter how much amount of weakly supervised pre-training you'll do, adding the small amount of pre-training is very useful. And the other thing we found, like because of MAE sort of asymmetric encoder-decoder design, is that actually this is flops efficient too. So for the same amount of training flops, using this pre-training strategy overall leads to much better performance for the same compute budget. And finally,
one more thing here. Sorry
yes.
for interrupting. Like I might be misinterpreting something. If you go back to the previous slide, yeah. So the size of this for the weekly supervised training that you're doing, the size of the data set is much smaller than the initial 5B. That's like 20K. You mentioned something. So when you're saying epochs here, I guess you're assuming epochs across that smaller, much smaller data set.
No, it's epochs across the 5 billion set.
Okay.
Yeah.
Okay, got it.
Yeah. So we're controlling for data. So there's no extra data being seen by either the pre-training approach or the pre-training approach. I think they're basically using the same amount of data.
Makes sense. Thanks.
And here, finally, we basically try to also see, like, okay, when you do this pre-training, does it actually, do a better job at different tasks? So MAE has shown to work really well for dense prediction tasks. So if you look at pixel segmentation, detection, MAE models are still like doing really, really well on these tasks. Whereas the weakly supervised learning methods do quite well on classification-based tasks, classification or retrieval or zero-shot, few-shot learning. And what we find is that basically when we do this pre-training with weakly supervised learning, it actually combines the strengths of both these methods. So now we actually start getting models that are going to do much better at both detection and zero-shot recognition, few-shot recognition, linear probing, and so on. And in general, when we published the paper, we actually had state-of-the-art accuracy for different benchmarks. And we also pushed these models out on GitHub. So if you get a chance, you can play around with them. The largest encoders have sort of been pushed out. And also the largest MAE encoders. So if you're just interested in self-supervised learning, you can also download just the MAE part. All right, so all of this sort of relied on this assumption that aligned data is sort of available. But in general, aligned data is not really that easy to get. So if you look at different modalities like depth, thermal, motion, audio, and so on, you don't really have very large amounts of text data coupled with them. So for example, for depth sensors, we don't really have a huge amount of depth data online anyway, not at least at the billion or trillion scale. But what we find is that whenever we're sort of capturing these depth, thermal, motion data, typically there's also an image being captured at the same time. So for depth sensors that exist on phones or even commercial depth sensors, they typically have an RGB stream coming through. The same thing goes for thermal, the same thing goes for like audio or motion. And this data is basically naturally occurring. It's self-supervised, so you don't really have to go out and collect it. And so in another work earlier last year, we showed that we can actually use all of this data together and use images to sort of bring together all of these modalities and train a universal embedding. And so the key idea here was that basically you have these images and videos that co-occur with different types of modalities. So what you can do is you can try to just align every modality's representation with that of the corresponding image that you observed at that time. And what ends up happening is basically because everything is being aligned to the image, we find this emergent property that after training, all these modalities get aligned together anyway, and you don't really have to observe any paired data for all of these pairs of modalities. So in this case, basically, we, for example, get the alignment from depth to text without ever observing a single pair of depth and text together at training, just because the text embedding is aligned to the images and the depth embedding is aligned to the images also.
How do you get all of these modalities aligned? Like, what does the data collection look like here?
So the data collection in this particular case, we actually just used off-the-shelf data set. So there is a depth data set called NYU where somebody just like took a Kinect and just like ran to like different places. And so you have like basically a large amount of video with the Kinect depth data, and you have the image data RGB stream corresponding to it. Same thing goes for thermal sensors. You basically can find lots of these data sets online where there are just like thermal sensors observing large parts of like an outdoor scene, like a road or something, and then you'll actually get the RGB stream from it correspondingly as well.
Makes sense. I guess because you're like Meta as a company works so much on the metaverse, I guess, and given you're making these devices, I was just like wondering whether you are also working on internal data collections or just leveraging those devices to just build better data sets as well.
Right. So I think for like IMU, it's pretty easy, right? So IMU is one of the things where like we are actually using the headsets that we have, and the ARIA headsets that Meta is building actually capture lots of these sensors at the same time. So you actually get RGB stream correspondingly with lots of other sensor data captured.
Nice.
And so once you have this, so the training setup in this work is quite simple. We have 6 modalities, and we'll only train with image paired data. So we'll exclusively use this. Of course, if you have some paired data with text, you can of course use that. But the point of this work was to really show that images by themselves are sufficient to get actually good performance. And so we'll initialize an image and text encoder with clip or OpenClip, and we'll keep that frozen. And then for every non-image modality that we have, we'll train a separate encoder. And we'll use a contrastive loss to just align the non-image modalities representation to that of the image representation. And that's it. So once you have this, you basically get this emergent alignment of all these modalities sort of being able to be aligned with each other. And so one of my favorite applications for ImageBind was basically just upgrading existing models. So let's say that you have your favorite model that only understands text, right? So you have a zero-shot classifier or a zero-shot detector that only takes text prompts as input. And of course, this is not fun, and you want to upgrade this model, but upgrade or like basically making this model understand different modalities really requires retraining this model, and that's quite expensive. So with ImageBind, you can actually upgrade this model without any retraining. Because the text embedding is aligned to all of these different modalities like audio, depths, thermal, and so on, you can just replace that text embedding with this with the embedding for your favorite modality. And now your model actually becomes multimodal by default. You don't really need to do any retraining. So as an example, we had a text-to-image model in-house, which just took text prompts as input. We replaced those text embeddings by these audio embeddings, and then we just plug that in. And we find that that model actually did a reasonable job of producing the images corresponding to the audio that we were feeding it. There was another thing that we could do. We could just take, for example, for retrieval, we could just add embeddings from different modalities and get some sort of multimodal reasoning. So here on the top row, you have a bird. You take the audio embeddings from waves and you add them together. And when we do retrieval now, the model actually is looking for birds basically in a beach-like scene because it is really using the audio from these waves to combine together the semantics of waves and bird. And now you basically are retrieving these things. And so here are 3 more examples showing this with like clocks and church bells, and then fruit with birds. So then basically the model is really trying to look for birds with fruits.
This is so awesome. Like it's not at all intuitive that this would be possible even like some years ago. Do you have an intuition why this works so nicely? Like that there is this common lower embedding space between all of these different modalities that can be shared and used to create these results? How do you think about this like intuitively?
Yeah, so I think basically, I mean, when we go around the world with like our multimodal sensor, which is basically our body, you see that like a lot of these things are extremely correlated, right? Like we are just tuned to do these things. You can close your eyes and you can just walk around. And if you hear a particular sort of audio, you can actually imagine what's going on, right? Like there's a lot of predictive behavior that's sort of built into you because you have a multisensory system inside. And so, yes, if it's dark, I can still kind of like do okay. If it's, if it's not as bright, I can still sort of do as okay. Or for example, I don't know, I came out of a shower and my ear is not working properly. I can still kind of go about my day all right. I don't like completely fail. So I think having these multiple sensors sort of builds the shared embedding automatically for humans. And I think that's basically what we observe over here. This data is extremely redundant and you do find lots of shared correlations between it.
Amazing. We have a couple of questions in the chat as well. If people want to ask them, you can do it yourself, or I can read them. Okay, so Marco asks, for audio to be converted to image, do you need to do FFT on the audio sequence? I don't think they're doing this, but go ahead.
Yeah, so we're not doing FFT. So we take the audio signal, the raw audio waveform, and then we just convert it into a spectrogram, a MEL spectrogram, and then feed that through the transformer.
Nice. How long does this alignment phase take in terms of pre-training time epochs of one of the models? Question from Data.
It's very quick actually. So because the image encoder is frozen, essentially you're just like taking your depth maps or something and just like aligning that. So in terms of epochs for depth, it depends on, of course, the amount of data. For something like depth, which in one of the experiments, we just used like 5,000 depth maps. We could get that done within 10 epochs and have a reasonable performance.
Nice. One question for me is, having observed what's been going on in the NLP space, and then like, how do you think now between dynamics between computer vision and NLP? And yeah, very high, like very broad question, but just wondering.
Yeah, so I think and that's where probably the next part of my talk will go to. I think NLP was really sort of trying to like generate things, right? And I think for a lot of the stuff that we were doing in vision, we were really trying to just like compress it down into the embedding space as much as possible without really trying to go back into the original data space. I think that does create some issues. So for example, for this aligned stuff, if I have a bird and waves and I'm trying to retrieve, but my data set doesn't really contain birds with waves, then I won't get anything meaningful out. It'll actually just try to do something random here. And so for even inspecting whether we're actually getting any alignment, you have to have a very large data set with all of these like compositions of concepts existing. Whereas for NLP, for a lot of these things, you can actually just probe the model. And because you're generating, you can try to just guide it to the right sort of subspace and then figure out whether it's actually learned something.
Awesome. I think there's a ton more questions coming in, but you can continue and then we'll pick them up along the way.
Sounds good. Sounds good. All right. So given all of this, I mean, the biggest question to ask is, are there other ways to use aligned data? And you just asked it right now, that what is like the similarity between NLP, or what is the difference between NLP and vision? I think really it does come down to that aligned data up until like a few years ago was really being used to power these aligned embeddings, aligned representations. And of course, the biggest elephant in the room at the time, and even now, maybe for some people, is generative modeling, right? Where you take all of these images and then you're trying to just learn the distribution of this data. And so for me personally, the reason I sort of really got into generative modeling is because I saw evidence from lots of other people, and also by like hacking around with a few models, that these generative models, the text-to-image models, for example, learn really useful representations. And so they have this very fine-grained understanding. So when you say, for example, like draw a cat with a yellow nose or a red nose or a blue nose, it actually does know what the nose of a cat is because it's able to change the color. So it understands so many different things about that image. And so just generating that image forces this model to have a very strong fine-grained alignment between language and between basically the image space. And you can sort of take that arbitrarily, right? You can have draw a cat with a yellow nose sitting on top of a chair which is blue, and so all of these things, basically you can just start composing things to an arbitrary level, and you do get very reasonable generations. And so there is something very promising about generative models because you're actually able to have such fine-grained control of the image, and maybe that can actually be extracted from this model back to demonstrate that they actually are learning useful representations about the world. And so very, very quickly, this is sort of my high level thinking. When we're training generative models, we're basically taking this input X, we're constructing Z by hiding some information from it, we're feeding that into a model, and then we're predicting X hat, which is basically our estimate of X. And then essentially during training time, you will take your target, which will likely also be the input X, and then you'll compute a loss between X hat and your target. And yes, there is the standard thing. Should we be doing generative learning? Should we be doing discriminative learning? I think if you come from the self-supervised world, both of them actually look quite similar. So this entire pipeline that I described of generative modeling, if you think about MAE is exactly doing the same thing, right? It's basically a denoising autoencoder where the Z that you're constructing by hiding information is essentially a masking procedure. And then you are reconstructing a target basically based on the input Z, which has a lot of information hidden from it. Of course, there are differences. I think the biggest difference basically being that in discriminative learning, we really care about different things at inference. So at inference for discriminative learning, we really care about encoding an X or encoding an image and trying to get a representation from it. Whereas for most of the discriminative generative models, we want to really sample from this P of X. So what we want at inference is a way to have basically almost no information in our Z or very limited information in our Z, and then really sample different things from our distribution. And for, of course, a lot of our work, we've been looking at diffusion models. These are the dominant class of generative models in the pixel space. And so here, the information is really being hidden by a Markovian noising process. And I think maybe all of you are familiar with like all the other sort of details that go inside diffusion models. So one interesting work that we had last year was self-eval, which basically shows that you can actually combine together generative models and discriminative models. And so I just have a one-slide summary. You can read this paper online. I hope you find it very useful. The one-slide summary of this work is that you can actually use diffusion models as classifiers to evaluate themselves. So on the left-hand side, we have a standard diffusion model that basically goes from noise, which is the sort of latent, and then you sample a lot of, with a different number of time steps, you sample and then you basically get an image. And here at the time that you're doing this, you have a text condition, which in this case is a dog. And then you're, of course, guiding that noise to basically become a picture of a dog by this diffusion sampling. In self-eval, we show that that pre-trained diffusion model can actually be used to estimate likelihoods of how much, of basically the likelihood of the image given basically your particular text prompt. So in this case, what you can do is you can take a diffusion model, you can feed it a real image, for example, a dog, and you can have n number of prompts, a dog, a cat, and blah, 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 a car. And then you can basically get an estimate for how likely each of these particular prompts is given this particular image. And so you can convert this diffusion model into a classifier. And what we show is that this classifier can actually be used to estimate how good your diffusion model is. So the classification ability of your diffusion model can actually be is very, very highly correlated with its ability to generate images given a particular text prompt. So how well basically the generated image will look given a particular complicated text prompt. All right. So given this sort of work, I do think in the future, we are likely to see more and more methods that are going to show you that all of these generative models that are coming out of even the vision domain are actually going to learn super powerful representations and really learn very fine-grained understanding of fine-grained grounding between NLP, sort of language phrases, and images or videos.
How does this compare with CLIP? Like this type of model, how does this model compare to CLIP when it comes to these zero-shot classification capabilities?
It actually outperforms CLIP on a bunch of tasks like Winnow-Ground. So Winnow-Ground is this like really challenging thing where you are, for example, trying to figure out are there plants surrounded by light bulbs or is it a light bulb surrounded by plants, right? So just like very simple permutation of the words changes the meaning completely. CLIP does not do a very good job at this. CLIP is essentially a bag of words sort of classifier when you're training it. And whereas something like a diffusion model, of course, if you were to give it these two phrases, will at least try to generate something different for both of them. And so for these very challenging tasks, Winnow-Ground, these types of models actually outperform CLIP.
Nice. And one question from Sriram, how about fantastic prompts, like out of corpus stuff? I'm not sure what he's referring to by fantastic prompts, maybe you know.
I'm assuming like unicorns or something which don't typically exist in the world. And so for this type of stuff, it actually does okay too. So you can actually have, I think what this basically shows is that diffusion models actually learn composition quite well. So when you say, I don't know, unicorn on top of a dog or like dog on top of a unicorn, it actually understands a bunch of these things. It understands these spatial relationships. And so when you do something like CLIP, you're actually losing a lot of that information. You're losing this sort of ability to figure out very small sort of nuances in the text prompt and how they affect the image.
I mean, but given that these models are trained often, like I'm fairly sure unicorns are actually in corpus.
That's true. That's true. So, yeah. I mean, I think like extremely out of like, I don't know, if you have like CCCCC, an animal which is basically 4 Cs and nobody else has seen it, of course, I think like nothing will be able to get it.
Thanks.
Right. So that brings me to one of our latest works, which we announced late last year called Emu Video, which is basically one of the state-of-the-art text-to-video generation models. And I'll try to walk you through what makes it unique. Like text-to-video generation has, of course, existed. There are lots of papers coming every single day out. And I'll try to talk you through why I think like what we discovered is quite cool. So text to video generation is a very simple problem. You have an input text prompt describing your favorite things, unicorns. And in the output, you basically have a video, which is hopefully related to your text prompt. If it's not, then this model is quite useless because, I mean, it's just generating video and not listening to you. So there are lots of these text to video diffusion models, right? So make a video being one of the examples from Meta, Imagine coming out of Google, Align Your Latents coming out of NVIDIA, and of course, stable diffusion video, yada, yada. There are like lots of these models coming out. Now, one thing that basically is quite different about like most of these prior text to image models, text to video models, is that they take a text prompt and then they're feeding it to a model, and the model is generating all of these video frames at once, right? And so if you look at the architecture design decision for like Imagine or make a video or even Align Your Latents, this is the very, very common pattern you'll find. So they'll always try to generate all of these n frames of video conditioned on the text prompt all at once. And of course, because there is very limited amount of text to video data compared to like text and image data, they all leverage a pre-trained text to image model. So all of this, like the blue bar over here, the model figure, is actually initialized with a text to image model. But unfortunately, you lose its style when fine tuning on videos. So if you have like all different types of styles, like fantastical styles, with photography styles and so on, in your text to image model, your video dataset is correspondingly going to be much smaller and may not even have all of those styles. So when you do this fine tuning stage for text to video, the models typically lose a lot of style information. So they'll try to generate only one type of video. So it'll either be like super realistic or it'll be like super cartoonish, but not get a whole range of all of these different styles. And finally, a lot of these prior works actually used deep cascades of models, something that is changing more and more. But just to give you an example of how deep these cascades could be, here is the sort of architecture diagram of Imagine Video, where you have a cascade of 7 different models that are actually going through. And overall, it's like a 16.25 billion parameter model. So you have an input text prompt, you have a text encoder, then you first generate a very sort of low frame rate, low resolution video. Then you temporally upsample it, you spatially upsample it, then you spatially upsample it again, then more temporal upsampling, and then finally more spatial upsampling to get to the final desired sort of video. And so each of these sort of cascade models are trained independently, and then they're sort of stitched together at inference time to generate your video. And this does make like iteration in terms of research quite hard, right? Like if I were to have, I don't know, more training budget or more data, which of these models am I going to spend the training budget on? Which one should I be doing this? And if I'm seeing particular types of artifacts, or if I'm seeing like particular types of lack of faithfulness or like lack of consistency, which of these models should I need to improve to basically fix that? And so having cascades, while it's sort of good because you can train all of them in parallel, it does make iteration time quite hard in terms of research because you're not able, it's harder to identify where do you want to fix certain issues. And one of our key insights in our work is that basically we want to use like factorized image generation. So the idea is basically that in the sort of direct text to video approach, you have this way of like taking a text prompt and predicting all the n video frames at once. This is quite different from NLP, right? Where you have autoregressive approaches. So if you were to ask a language model to generate like 1,000 tokens, it doesn't predict all those 1,000 tokens at once. You always try to basically take your condition, then you try to predict the first token, then you take that, then you predict the next token. And so what that means is for every future prediction, there's always a stronger conditioning, right? So for the second token, you already are conditioning on the first token that you've predicted. And so the distribution that you will sample for the second token is already sort of more constrained than it was for the first token. And the same thing holds for the third token, the fourth token, and so on. So the conditioning kind of gets stronger as you're doing this prediction. Whereas for the video prediction, it's kind of weird. We're basically also in a very high dimensional output space where we have HW, which are height, width, and time, the temporal dimension. So HWT, number of pixels that we're trying to predict. And we're predicting all of them at once, just conditioned on this text prompt. So we're modeling a very high dimensional output space. and we're not really, we don't have any mechanism for improving the conditioning. And so autoregressive is really sort of I think, a very good way of solving this, where you are trying to do this one step at a time. Unfortunately, for diffusion models, because for diffusion models, when you're trying to sampling is quite expensive, right? So to generate even one frame out, you're going to do least number of steps of sampling. So, and this makes autoregressive very hard, because it's going to make it super slow at inference time. So in this previous figure that I had, for each step of autoregressive, when I'm trying to basically when I'm trying to sample each of these video frames, I will have to run n number of steps of diffusion. So correspondingly, so for the first frame, for example, I'm running 50 steps of diffusion sampling. For the second step, I'm also running 50 steps, and then for the third one, also 50 steps. And so by the time you get to like 10 frames, you've already been, it's a very slow sequential process, and it makes inference very slow. So our key idea over here was to basically factorize this entire generation process by explicit image conditioning. So we want to enjoy the benefits of strong conditioning, but we also want to make this process quite fast in terms at inference time. So rather than doing directly like these n frames, we're going to first basically take our text prompt, take the model, and predict a starting frame. So that starting frame already basically contains a lot of the information that you want about the text prompt. And now in the second stage, we'll condition on the starting frame and the text prompt, and we'll predict all the n number of frames after that in parallel. And this second stage is slightly easier, right? You can think of this as like an image animation stage, where you have a lot of the content of the image already created for you, and you're just predicting how that image will evolve in the future. What type of things will sort of change? You're not really worried as much about the composition of the scene, just about how it's going to evolve into the future. Whereas in the left-hand side, on the direct text-to-video approach, you're deciding on both the scene composition and how it will evolve at the exact same time. And so Emu Video is basically a single text-to-video diffusion model. There is no cascade in it, and it automatically supports image-to-video animation because of the way we've sort of trained this model. So the same exact model can do text-to-video, it can do image-to-video, it can do text plus image-to-video. And because of certain design decisions that we took, it can actually retain the style of the pre-trained text-to-image model trained on billions of images. So now you can actually generate your favorite videos in like n number of different styles without really having to without having videos of those particular styles. And there is a paper out. I'll just try to give you a sense of what the temporal parameters are. This is quite standard now in diffusion models, especially for video, where you take a pre-trained text-to-image model, which has these 2D parameters, so a 2D convolution, a spatial attention, which has a cross-attention to your text prompt. And then you add basically these temporal parameters that are learned. So you add a 1D separable time convolution, and you add a temporal attention that's also 1D, so it's going to perform temporal attention just across the frame. And these parameters that are shown in red are the only ones that are trained, whereas the parameters that are shown in green are the ones that are fixed, so we do not train them. So essentially, we're training very few number of parameters when we are learning this video model. So here's a final architecture diagram. You have your input noise. You have a particular text prompt. You feed that to the model. You first get a starting frame. And then we basically take that starting frame. We concatenate it with a mask that tells the model to only sample future frames and not the first frame. And then we concatenate it with that noise. And then we feed that to the model again. And then it generates basically the full number of like frames, the full number of videos. And in particular, for the architecture we use for this paper, we had 2.7 billion spatial parameters that are frozen. So it's a pre-trained text-to-image model called EMU, also from Meta. And we have 1.7 billion temporal parameters that are learned. And we'll generate 16 frames at 4 FPS, 4 seconds. And if you want a higher frame rate, then we can have a second stage of an interpolation model that can convert the 4 FPS to 16 FPS.
Just to understand here,
few sort of
for the initial frame and for the subsequent frames, do you use the same model, or you just take a component of out of these two?
So it's the same model. Yeah.
Got it.
So
okay.
What you can do is basically for the So for the first stage, we basically just skip when we're trying to predict the first frame. We just skip basically the temporal parameters. So it's just going to be the spatial model, And because that's frozen, essentially it does not forget how to generate an image. And then for the second stage, basically when we're generating all the n frames at once, we use all the parameters of the model.
Nice, thanks.
And so here are a few sort of videos that we can generate. You can do them in various different styles. They can be super realistic, they can be futuristic, and you can see that like for example, on the left-hand side, left-hand bottom, you have a camel sort of being a DJ. You see that if you're actually getting articulated limb motion, which is quite good. You have, for example, a papercraft dragon going through waves in like an 8-bit video game style. And so it actually retains lots of different styles of video, from like super realistic to like video game style to 8-bit like artistic style to like painting style and so on. And for all of this, we don't really have to have videos of that style, just because we're leveraging a very powerful text-to-image model, and our training and the way we're doing inference actually retains all the styles from this image model. So coming to a few results, for most of the evaluation in this paper, we really relied on human evaluation, because we found that the automated metrics that are typically used in prior work, so which are, for example, FVD, which is a fresh air video distance, or like a clip score and so on, are extremely unreliable at predicting quality. And in fact, for most of the experiments that we had, FVD was not really telling us whether humans like a video or not, and it would not really talk about whether there was a step change in quality. And so for all of these things, you'll basically see that in the following slides, I'll report two numbers, which will be quality and faithfulness. So we take basically videos. For example, you have direct and factorized. So we'll show these pairs of videos, and we can video do they prefer in terms of quality. And for faithfulness, they're basically saying that which video do they think aligns better with the text prompt compared to the other one. And so in this particular case, we are trying to compare basically direct generation, which is where you're predicting all the n frames at once, versus our factorized approach, where you're basically first predicting the first frame and then predicting the future. And what we find is that humans prefer basically our factorized generations 70% of the time in terms of quality, and 63% of times basically in terms of faithfulness, which already shows you that basically factorized methods are doing much better. And for this particular comparison, the direct model has the same exact model capacity, uses the same exact training data, so the same like image training data, the same video training data. So it's all like apples to apples comparison. And despite that, we find that basically the factorized approach is doing much better.
Nice. This is impressive. You cut out for a moment. I think your internet dropped, so I didn't get to hear how exactly do you compute these metrics?
Right. Okay. So basically, in this case, what we'll do is we'll show humans these pairs of videos, so the direct video and the factorized video, and then we'll ask them to basically pick one of them or the other. So they'll essentially, it's like an A/B test, right? You're showing A versus B, and the human evaluator is clicking which one they prefer. So for quality, the question is basically asking them, which video do you prefer in terms of quality? And for faithfulness, we're asking them, which video do you think better respects the text prompt? So it's basically measuring the text to video alignment.
Got it. Makes sense. The thing I was getting at is I'm thinking about what's happening in the NLP space is something like here, the equivalent would be having like a VLM as a judge or something. Like, are you guys considering something like that? And like, it wouldn't be unimaginable that people start using, I don't know which VLMs you guys have, but like GPT-4 with vision as a VLM as a judge or something to scale this up, because ultimately you can do it differently.
Yeah. So I think VLMs actually, so we have tried a few VLM, like VLM style metrics. They work quite well for faithfulness, where you're measuring text and video alignment, but typically not so much for quality, right? Because for quality, you're really looking at, okay, are the hooves of the horse or the unicorn in this case landing properly in order? Is it sort of realistic? Are there glitches? Are there like any sort of shimmers? Are the clouds moving realistically? Is the sun rising realistically? This type of stuff, I think VLMs aren't really good at even now. Like, you really require very, very fine-grained understanding for this.
Makes sense.
All right.
But then again, if a VLM knows how to generate, like if you have a really powerful VLM that understands the nuance of the language and can generate that, like, it's theoretically just completely imaginable that we're just not there right now, maybe. But
yes,
yeah.
yeah. I think we are just not there right now. I think that's basically why human evaluation is probably the sort of easiest thing to do right now. I hope that in the future we can rely on models, because yes, it's pretty hard to scale human evaluation. Also, you really need to be very careful about the guidelines you give human evaluators, because depending on the guidelines, you might actually get various different results.
Mm-hmm. How do you guys deal with fingers in these videos?
So I think the base model that we have, EMU, actually, so there's a separate paper about EMU. EMU does quite well on fingers, I think, or humans, because they really try to train on that type of data or like a very large distribution of data. And I think that really sort of fixes a lot of these errors. So I don't think there's a huge amount of special modeling done for dealing with like fingers or something. It's just that if you have a reasonable data distribution, then you can actually get around this problem quite easily.
Nice. The fingers module or the fingers neuron.
Yeah. Maybe it exists inside the model, but I don't think you really have to do anything special, at least not that I'm aware of, for either our work or the EMU work, for which you had to do anything special for just handling fingers.
Nice, thank you.
Cool. All right. So the other thing that was quite surprising, and I think this is one of the main things that makes our approach work, is basically this sort of persistent issue with diffusion models. So if you think about diffusion models, you're actually adding noise to them to basically go from like a pure data distribution to a pure noise distribution. And what happens is, for a lot of these models, the noise schedules are actually optimized for a low resolution, which is 256 pixels. So this even is a problem, for example, in stable diffusion. The noise schedule was really optimized for the 256 pixel resolution. And if you look at 512 resolution and you add the same noise schedule or the same amount of noise, there's still some structure preserved basically at the sort of higher noising steps. And in fact, it's not perceptible to human eyes, but even at the last sort of stage, the ultimate stage where you expect basically the input to be like complete noise, it doesn't really have complete noise. There is still some signal remaining, which is basically you can show it theoretically by measuring a signal to noise ratio for diffusion models. And there's this excellent paper earlier last year, which actually showed this for various different types of image models. What we found actually is that so this paper really showed this for image models and said that this is one of the reasons why you can't really sample super dark or super bright images. And so it really was trying to fix aesthetics basically for images. What we found is that for video, it's actually not even about aesthetics. Without fixing this issue, you really cannot generate high resolution video directly. And that's mainly because when you have, say, some residual signal, let's say 1% of the signal is sort of remaining in the image. For video, you're actually multiplying that by 16 because you have 16 frames that we're dealing with, and there is a huge amount of redundant information across these 16 frames. So even if you have 1% sort of remaining signal in one frame, you actually have 16% remaining signal in your entire video. And it's actually 16% IID, right? So if, for example, one of the pixels in frame number 1 was masked or like noised properly, but it was not noised in the second frame, essentially you can just like copy over the pixel value from the second frame to the first one. Most pixels aren't moving around by that much, and you can basically reconstruct the entire video directly. And so what we found is, if you do not fix this issue, the diffusion models really produce like very bad videos when they're trying to produce high resolution videos. And here's basically a slide showing this. So at the bottom, we have basically fixed this issue. We've changed the noise schedule to make sure that there is almost no signal to noise ratio at the very end. And at the top, we haven't fixed this issue. And when we're trying to sample from a model that hasn't fixed this issue, you get like really jarring videos where the dog sort of disintegrates into nothing. Or for example, where the sort of tortoise also disintegrates into nothing. And when you measure this by human evaluation, of course, like as expected, 96.8% of the times people prefer the model that was trained with 0 SNR versus a model that was trained without 0 SNR.
That gives you the baseline for the trolls, because
yes, exactly.
Yeah,
exactly. And finally, what we found is that after you've sort of pre-trained this model, you can actually improve the motion in these videos. So both the motion quality, the amount of motion, and the consistency by sort of fine-tuning it on high-quality motion videos. And so for doing this, we just automatically extract basically high-quality motion videos. So we just like look at automated signals. So the amount of motion present in videos and sort of how sort of good the text to video alignment is. And we identify a very small subset of about like 2000 videos from our pre-training set. And when we just take our pre-trained model and fine tune it on these 2000 videos for a little few number of iterations, and then we find that that significantly improves the motion quality and the consistency that we can generate of these videos. So for example, here we have on the top row a model without fine tuning. And so you see that the motion is not maybe as consistent. Also, there's little amount of motion. So like the ears of the dog are sort of like moving independently of the dog's face. Whereas in the bottom video, you actually do see that now the camera is actually moving in, the dog's paws are moving properly and so on. And that same thing exists, for example, for the unicorns and the turtles. And in terms of human preferences, this actually improves quality and faithfulness, both faithfulness by quite a big margin. So like almost 80% of the users favor basically the fine-tuned videos compared to the original videos. All right. And here are a few qualitative comparisons basically between like different methods. Of course, the one issue with benchmarking is that not a lot of these models are public. So what we did is we basically just rely on the public videos released by the methods. And then we just use that same text prompt to produce videos with our model. And then we just ran an A/B test to compare the previous generation with our generation. And in our case, we did not really optimize the generation for these prompts. We just used a simple fixed seed to generate whatever the video was generated. We just used that. If you're releasing these videos on your website, you might have done some cherry picking. In our case, we didn't have that option when we were comparing to other methods. And so here are human evaluations, basically comparing EMU video to different methods, commercial systems like Pika Labs Gen 2. You have Cog Video, Imagine Video, Maker Video, and so on. And basically, we observed that across the board, we are able to have a pretty high win rate percentage. And these are all basically the same quality faithfulness evaluation that I was talking about earlier. And so we do find that EMU video generations are actually quite good. And human evaluation confirms that this is one of the video generations that actually look really, really good.
Did you maybe see the recent project from ByteDance, Magic Video V2? It was just released a couple of days ago. How do you think that compares with EMU video? So, because it came just recently.
Yeah. So I think one of the issues, of course, is that when people release videos, it's very hard. Like from like, I don't know, 10 samples or like 15 samples, it's very hard to figure out which one is doing well or not. And so typically, I think like staring at like a very small number of videos doesn't really tell us a whole lot, because I can pick arbitrarily any 10 videos that make my model look better versus the other model and vice versa. So we're still going to like run some evaluation to see whether this happens, like what the quality is. A priori, it's a little hard to tell.
Yeah, that's kind of disappointing. I mean, understandably so, because everybody's pushing for commercialization, and then research is kind of turning into a PR and like selling a bit, which is unfortunate. But yeah.
And so, like I said, our model can actually be used to animate images, the same exact model, because we can just take an image and pretend that that was the first frame that was generated by our model, and then just feed that into the model to generate basically this video. And here, basically, we have like a few of these images that are being animated or brought to life. So you have like the Titanic, you have the cave paintings, you have I think for some reason the videos aren't playing. I'm not sure if you can see them. Yeah, okay. Yeah, so you have like the moon landing sort of moving around. So here's finally like a video that we released, which shows basically different style generations from our model, like different types of clips, and how it can generate prompts with different concepts. And so here we're sort of really composing different actions with the same exact actor. So here it's a corgi doing different things in different scenes. And again, different characters.
Nice.
So yeah, you can find these videos basically online, and more of these. I think I'll just stop here. I have one more thing, but I know we have like 2 minutes.
Nice, awesome, Ishan. This was super cool. What's the red dot there? Is that where you're located, or?
No. I think this is where, like, this was a video. I think we posted. It's called Frosty, which basically is like a character we made, and then we just like created a story based on Frosty and video clips generated with emo video.
Nice, I'm joking. Otherwise, it would be very, very cold where you're based.
Yes. Right.
Cool. I think I'll also have to wrap it up because I have hard stop in 1 minute. But this was amazing. Really happy you had the time to join us. And if people have more questions, and I know you did, I tried to cherry pick some of them. Maybe if Ishan has some time, you can like answer in Discord now or later when you find some time.
Yeah.
Awesome.